Hello, I'm Weiwei. I work on the Mojo language team at Modular. Today I'm going to talk a little bit about what we've learned from building Mojo's compilation optimization pipeline. Just a quick overview of my talk today. We will first take a glance at the Mojo language, and then a general view of how the compilation pipeline looks like. And then we will dive deep into the two parts of the pipeline, the MLIR part and the LLVM part, and share a bit the things that we've learned from building these two parts. And at the end, we'll have some discussions and questions. Just a quick overview, a quick look at Mojo. So Mojo is a new Pythonic system programming language that was firstly announced early last year and is still very actively under development at Modular. If you take a look at the right side of the slide, it has this Pythonic kind of aesthetic of the language and has a lot of Python compatible features. So in addition to that, Mojo also has some superpower features like extensive generic programming capability, type system, safe, efficient memory model. It gives you C-level kind of control in terms of program performance. We also support a general kind of heterogeneous programming model so that you can write both CPU code and GPU code all together with synchronous programming. So some of my colleagues are gonna talk a little bit about some of the new features that we are adding to the programming language, both today and tomorrow. If you're interested in the details, these are the great talks to go to. But today we're going to more look at what's the compilation, how does the compilation look like. So the Mojo compiler is built based on top of the MLIR framework with LLVM as a backend. So here is a general kind of flow of the compilation. We have the Mojo program, .mojo file, first go through the Mojo parser, and then we will enter the IR, which is in the parameter domain. So this is still generic. So we will pack some of the library code into Mojo package, which can be used later by other programs so that we don't have to go through the parser again. We will do some optimizations in the generic domain. Then we will enter the elaboration phase. Elaboration is kind of a Mojo-specific term. It's pretty similar to C++ template instantiation. So we will run a bunch of interpreters and try to materialize the IR. After the elaboration, we will get to materialize the IR. We will perform a little bit more optimizations and then translate the Mojo dialogues that we have into LLVM dialogues and then use the LLVM infrastructure to go to the final binary code, targeted code. We also do a little bit more things here, kind of using LLVM in an unconventional way. I will expand into the details a little bit in the rest of my talk. Mojo also use a library-driven compilation model for heterogeneous platforms. So for GPU code, when you write the GPU code, you will always write some like host code in CPU and then the GPU part and then maybe some other host code. So in Mojo, GPU part is a parametric function. That's why the GPU-related compilation happens during elaboration time. Instead of running the interpreter, when we try to materialize the GPU code, we run a code compilation for GPU. So this part is pretty much similar as the main part here. I'm just like briefly, because I want to put it on the slide. And then we generate PTX code as the result for elaboration, plug it back into the elaboration phase for the host code, and then go down. So as most compiler needs is like the goal what we want to achieve for Mojo compilation is that we want a fast compilation time, and we also want to generate performant generated code. But a few things that we've found when we first initially implement the compiler, that what we figure out is that LLVM pipeline actually takes a really long time in the overall Mojo compilation time, about 60 to 80% of compilation time. And as you can see from the time tracing here. We also figure out that O0 compilation time is an order of magnitude slower than O3, which is a little bit counterintuitive because O0 we are running way less optimizations. It's supposed to generate less performant code. But now we're taking longer time and generate worse code. That's not great. So what we've figured out is that, first of all, Mojo has very extensive generic programming support. This actually leads to like a really large IR size after elaboration. So it's kind of a code size explosion. And especially for O0 versus O3, O0 is actually significantly larger. The IR size is significantly larger than O3. As you can see, some of the profiling data here, before LLVM optimization, O0 is about 10x larger than O3. And after LLVM, some of them are like about 100x difference. So for O0, when we have a really large IR size, it put a lot of pressure on the whole compilation pipeline, both the LLVM part and the MLIR part. So with that in mind, with all these observations, what we are trying to do is, at the MLIR level, because we have full control, we are building that part. We're trying to replace some of the LLVM optimizing passes and try to really grinding down the IR size every step of the way so that we don't have to send a large amount of IR to the LLVM pipeline and make that pipeline to do a lot of work. So we have a bunch of optimization passes at the MLIR level, including mem2rec, throwa, SCCP, loop unrolling, stack reuse, simplifies CF. These are very similar to what LLVM has, but we kind of lift them earlier to the MLIR level so that we can keep the IR size in check while still like doing all those performance-related optimization. We also have some functionality-specific lowering passes at MLIR level, for example, for closures and async coroutines. We also run some of the basic passes, including canonicalizer, CSC, and eliminate dead things. So in addition to keep the IR size in check at MLIR level, implementing some of the optimization at MLIR level is also very beneficial because we have a higher level IR representation at MLIR level. For example, we have IR representations of async coroutines like stack allocation, some operations for variety packs. So they have more meaning to the program, which can help us to simplify the implementation of the optimization passes. At MLIR level, we also have a region-based structured control flow representation, which is different from the generic CFG that we usually have in LLVM IR or generic MLIR, where you have straight line code in basic blocks and just branches at the end of the basic block. So we have this structured control flow representation where you can see that we have a loop, we have if, and we can have like early exits in the middle of the regions so that it matches better with the kind of higher level representation with the program logic. This actually really helps us to guarantee some of the best case scenarios when we implement data flow analysis like SCCP and mem2rec. And moreover, when we try to implement the passes at the MLIR level, we also really focus on parallelization. That is mostly for compilation time. First of all, MLIR framework has just natural support for parallelizing function up level passes. So we just need to make sure that when we create the pass manager, we will add the passes accordingly so that we can just automatically leverage the parallelization provided by the framework. We also, when we implement those inter-procedure optimizations like module up level passes, we also try to inject the intra-pass parallelizations to parallelize them. For example, for the inliner that we have at MLIR level, we really try to implement it so that within the passes we have parallelization. For example, when we inline a call graph, we want to do it from bottom to up. And we want to inline the call list for every function. And we create that, for every function, we create asynchronous kind of parallel tasks. And we set the dependencies between the functions if there's a call graph dependency along them. So if they have a kind of pass to each other, they have to wait for each other to finish. But if there's not direct pass between the functions, they can actually run in parallel. For example, here in this very simple call graph, F1 and F2 can run in parallel, and the foo and bar can run in parallel when we inline them. And we also try to apply the similar kind of approach for the elaboration part, just like really trying to bring up the level of parallelism in all the optimization passes that we have at MLIR level. This really helped us to improve the compilation time while not to lose too much generated code performance, because we are also doing optimizations like for memory, data flow analysis and things like that. And also more importantly, keep the IR size in check. Now let's take a look at the LLVM pipeline. We have the MLIR part, but we don't want to re-implement everything in MLIR. We still want to use the powerful part of LLVM pipeline. So LLVM is very good with things like scalar optimizations, the load store optimizations, and LLVM is very good with target-specific code generation. We don't have to reinvent the wheel. We still want to keep those things. However, LLVM is not super desirable, right? It's not perfect. Like it has kind of weak and unpredictable loop optimizations. There are a lot of heuristics. It may happen, it may not happen. From program's perspective, you don't really have a lot of control for that. And also, more importantly, LLVM is single-threaded. It's not parallelized, so that it's very hard to leverage the multiprocessor, what we have in modern machines. So what we do when we are constructing the LLVM pipeline, we try to really simplify it so that LLVM does less work, only do the important part. So we remove the vectorizer, we remove the loop enroller, and we move those functionalities up to the Mojo library. So you control that when you write the program. We disable coroutine related passes because we can implement coroutines and stuff at the MLIR level. And we also try to disable all the interprocedure optimization passes so that we can create like per function LLVM pipeline and run them in parallel. I put a question mark here because it's not exactly what happened. So we try to implement that, and then we realized that actually inlining is quite critical for generated code performance. So we get rid of the LLVM inliner, we get rid of all the IPO passes, and we figure out that for some of the benchmark models that we're running, we get about 2x slowdown without LLVM inliner. We can actually recover the performance with very aggressive inlining strategy at MLIR level. So we do have a MLIR level, kind of higher level inliner. If we become very aggressive there, we can actually get the performance back, but there's a cost that we're paying. As you can see here that with aggressive inlining, the CPU utilization is higher because we have more parallelization happening, but the memory also we need more memory because the code size is larger. And overall compilation time is more or less the same, so it's not quite helpful. So it might be a little bit naive to think that we can just get rid of LLVM and replace it with amounts of work building that at MLIR level. Conclusion here is that we still need LLVM inliner till we can build a kind of equally sophisticated one at the MLIR level. So with that in mind, we still want to parallelize the LLVM pipeline. So we kind of choose a two-level parallelization splitting strategy to parallelize the LLVM pipeline. So to parallelize the LLVM pipeline, basically we just try to split the LLVM module into multiple submodules and try to run the whole pipeline on those submodules in parallel, right? It's like splitting the CPP file into multiple ones and compile them in parallel. We do a two-level splitting. The first level is that we split the unoptimized LLVM module into subgraphs, and each subgraph will keep the full function call graph, so that when we run the optimization, we can still run the inliner and they can see each other. We keep the optimization at that level. And once we optimize everything, we split the subgraph further into functions. Then we run the codegen part for every function in parallel. So it's like a further parallelization. And at the end, we will put the output together. So as an example here, we have LLVM module, which has two functions, foo and bar, both called in G and H. A very simple example. Real case is probably G and H is going to be optimized away, but as an example, I'm going to show that they will stay there. So the first step is to split the LLVM module into subgraphs. Here we have 2 subgraphs, full and bar, and we keep the full call stack. So we have G and H here. There's a little bit issue because you see there are duplicated code, right? G and H are duplicated. And then with the subgraph, we will run the optimization, and we get optimized modules. Then we further split optimized LLVM modules into per function. So here now we have full and G and H and bar all in separate modules. We can run this with CodeGen. However, the duplicated code is still here. And for full and bar to see G and H, we also have to change symbol linkage type from internal to weak so that the linking can, the function will now be optimized away and then the call will fail here. So this is not perfectly ideal because we have duplicated code, we have to change symbol linkage type. So we actually add an extra layer of, we are kind of doing something very unconventional here. First of all, when we run the CodeGen part, which is similar to LLC, we run the full CodeGen doing like instruction selection and stuff like that, but we stop right before ASM print for each split. Then we build this thing called MC link, which will link the CodeGen result in memory. It will do a bunch of reduction kind of work to bring all the like constant pool IDs and global MC symbols into one MC context. And then we just run ASM print as one thing and for the linked result so that we can fix the, we can get rid of the duplicated functions and we can fix the symbol linkage type. And now we have one LLVM module as input and still one .o as the output. It's kind of a very unconventional way to use it. We would love to upstream this because we also run into a bunch of infrastructure issues. I believe that if we can upstream this, folks in the community can use it. It can also keep this part more stable in the tree. So with this special MC link, as you can see that for the generated object code, we don't have duplication anymore. G and H actually are gone because they are internal functions. You should now see it in the symbol table in the output object file. So everything is being fixed. Great. We do run into a bunch of infrastructure challenges while trying to parallelize LLVM. First of all, it's because LLVM is not thread safe. So for things like LLVM context and MC context for optimization and CodeGen, we have to make sure that we have separate copies for each split when we run the compilation in parallel. And we have to make sure that the IR are being moved into those contexts in an efficient and also safe way. So we use actually LLVM bitcode to serialize and deserialize those IRs for the migration between different contexts. We also run into some inefficiency in LLVM bitcode that, for example, characters are actually encoded as uint64, which takes about 8x space as needed. It is also not super performant to do the copy of the strings. And lazy loading is also pretty great for function bodies, but not great for constants. And we run into a little bit of performance issue with PTX because PTX currently now we're using it as basically just a big string in the IR as a result of the elaboration. So we have to somehow work around these issues, try to not fully rely on the infrastructure to do that. And for linking at the CodeGen level, a similar issue that we have to, when we link them together, we have to put all the splits back to the same LLVM context for linking. So there's another serialization, deserialization happening. The target machine that we use for CodeGen is not stateless, so that we also have to keep multiple copies for each split. That actually increase the kind of memory footprint during CodeGen. And also for target-specific backends, we have to do some small modifications for the reduction, and most of them are private APIs, so it's kind of challenging to change or access from off-tree. As a conclusion, what we figure out when we build the Mojo pipeline is that, first of all, compilation time is a function of IR input size to LLVM instead of the amount of work that we want LLVM to optimize for. So to address that, we move a lot of optimization passes earlier at the MLIR level so that we can progressively optimize the IR and choke the funnel size to keep the IR size in check. We also have higher level representations of the IR so that it helps us to simplify some of the implementations of the passes. We also try really hard to leverage the parallelization inject parallelization into the passes. We are kind of using LLVM in a pretty unconventional way. We do this two-level parallel level of splitting and try to do the MC linking to make sure that we have parallelization. We also have like a right cogen result. So as a result, today LLVM pipeline takes about 20 to 30% of compilation over overall Mojo compilation time. So as a conclusion, we think we can build a compiler to leverage the best part of both MLIR and LLVM. We don't have to build a compiler purely in LLVM or purely in MLIR. We can have both of them work together. Thank you very much. This is the end of my talk. Any questions?
Any questions? You have mics here, and I can bring a mic to you.
You didn't talk about the runtime performance impact of this. Would you have any numbers on runtime performance?
Runtime, you mean when the code is being run?
Yeah.
I don't have that because this is mostly for compilation. Yeah, sorry.
So when you split into subgraphs, right, and you kind of you duplicate the functions sometimes, right?
Right.
But you split to parallelize to improve the compile time, right? But then if you duplicate, then the compile time of each subgraph is going to be regressing, right? Mm-hmm. So what's your approach to solve this?
Not very sophisticated. We do try to sort the IR size kind of as an estimation for how long it will take for the optimization and try to balance the workload. But right now we're just creating like a parallel tasks and let the runtime system that we have to schedule the code. So it's not just we are creating threads. We actually have an async runtime system. We just create tasks and the runtime system will schedule the workload to balance the workload.
Sorry, I'm curious if there's a module size below which you don't see a benefit to further parallelization. You know, like what's the minimum granularity that you would want to make modules before you give up and say, I'm not going to bother parallelizing anymore because of the overheads would dominate the speed up that you get from parallelizing?
This is actually a very good question. I don't think we have like a really grinding down to that details yet. I do see like when we have too many parallelizations, which is kind of overwhelm the system, right? In a sense, like we always say parallelization is kind of a scam. Like it's only beneficial when you have enough resource to run it. If you don't have enough resource, parallelization adds overhead, so it may not be beneficial. That is something that we definitely should, when we do the fine-tuning of balance the workload, is something that we should work on and figure out the details.
So are you generally compiling relatively large programs in a compilation unit, or are they smaller, or?
Most of the things that we're looking at are ML graphs. So machine learning things, they normally will have at least like 100 functions. So per function, we have like really enough level of parallelization to leverage. For this tiny example, it probably doesn't make a lot of sense because there are only 4 functions.
Okay, thanks.
Yeah.
In this example where you're showing how you're cloning functions, I was wondering what the trade-offs are with having internal linkage copies versus making all of these copies be available externally, and then having a separate module that contains discardable copies, if anything, that would have been duplicated?
In terms of copy-wise, it's not mostly the critical thing here. The reason why we keep them duplicated within the module is because we want inliner to be able to see the body of the function so that inliner can actually do things about that. So IPO, like interprocedural optimization, can still do that. Of course, like as what Rust does, like we can just keep them all as separate and external thing and do LTO level kind of optimization. But LTO is not as optimal as doing the things earlier.
Yeah.
Yeah.
I was talking about available externally linkage specifically, which I think in theory is supposed to make the body available for inlining, but still tells LLVM to not actually code gen it.
Oh, you mean to tell LLVM to go to check the external bodies?
There's a linkage type called available externally where you're providing the body for IPO purposes, but it still shouldn't get code gen. I'm sure there's some reason that we can talk about it later.
I don't know that yet, but I will definitely look into that. Thank you very much.
Quick question out of curiosity. Have you looked at pass-level parallelism? There was this project in GCC a few years back when they parallelized different optimization passes, and they basically ran this as a job system with an optimization pass depending on another, constructing like a task graph, and they found a fairly good speed up from that.
Right. I think this has been mentioned, and the keynote is like LLVM Pass Manager is moving towards that direction. However, it's kind of really hard because LLVM data structures are not thread safe. So to make that work, we have to like very invasively make amends to the data structures, because when you run things in parallel, if the context is not thread safe and you're mutating the IR, bad thing will happen, right? There's a race condition. So in addition to parallelize the passes, we have to make sure that the data structures are safe. MLIR is much better than that because the framework supports that. As long as you create like isolation from above, then you can do that. LLVM is moving towards that direction, but not quite there yet.
Thank you.
Yeah.
Thank you. Thank you, Weiwei, again.
Thank you.